really appreciate you guys helping us host back here. I can take us to another location if those guys are busy, but we really appreciate Veritas hosting us yet again. So I'm happy we can do that. Let's see, any housekeeping stuff? I think we're going to nominate June as I think June or I don't know. It depends on when Brian shows up. We'll find out what's going on. But 10 years we've been doing this. Wow. So it's pretty cool. And so we're going to celebrate either May or June. We may be social. That just may be us being social afterwards. We may, I don't know, maybe we'll do a barbecue at somebody's house. I don't know. But we'll just watch the website. But yeah, I'm excited to think about 10 years. I've only been doing this, I think I started helping out Brian in 2011, but he did it, at highs before, and it's just cool to see like a decade already. So look for that. If you have any ideas on where to go, what to do, that's always appreciated too. So next month we do not have a topic yet. If somebody wants to, I think we've got something set up for June. We've got Jack coming in with a 3D printer, and he's actually going to set it up, calibrate it, show people. If you haven't seen one, see how it operates. I think he's willing to show that for June. But for May, we don't have anybody. So if somebody has a topic that they'd like to share, come see me afterwards. I can always have an open QA as well if people are interested in that. So tell me about that on May. And yeah, that's all the paperwork stuff. So Andy came here, what was it, August last year?
Yeah, it's a while ago. Sorry, yeah. I've been missing all your meetings.
It's all good. It's all good. So he came and presented a bunch of stuff about FPGAs, and so I showed the cool lasers, and yeah. So I think that we were in the other building that day, so we were kind of cramped. Now we've got a little bit more space, but we've got more people, and it's really cool. I really appreciate the work that you do and what you're going to be showing us today. This is where I would say the innovation for Linux is really happening these days. Not to say that our distros are dead; they're active, but you can see a lot of the that divergence here coming from Linux, where the professional server marketplace and the desktop is kind of maturing. You see those things happening, but you also see a lot of churn away from that. Where you see all the hot stuff is IoT and embed, and yeah, I'm excited that you're going to show us today. So cool. Anyway, without further ado, Andy's going to show us some Yocto.
Yes, sir. Yocto Linux. Cool. Well, thanks guys for having me. My name's Andy Gickling. I've been doing Linux probably for less time than this meetup group has even existed. So it sounds like you guys are at 10 years now, and I don't even know that I've been doing Linux for 10 years. So really interesting stuff. But learned a lot over the years, and I'm really excited to tell you guys about Yocto Linux. I'm going to try to go for about an hour and a half, and if you guys have any questions while we go here, don't hesitate to stop me and ask the questions. So, who knows what Yocto Linux is? Who's ever tried it before? Raise your hand. Yeah, got a couple hands. Good, good. Who's heard of it but has never tried it? I suppose a lot of you have heard the term. Okay. So Yocto Linux is well, this whole presentation is about Yocto Linux, and it's another form of Linux, and we're going to tell you basically all the details of how it works, and we're going to get you started. So if you wanted to go home and try this on a Raspberry Pi or whatever, you'll be able to do that. So background, we're going to talk about the motivations for Yocto Linux. After that, we're going to talk about what it is exactly, how you use it. We're going to talk about supported platforms in case you want to try it yourself. And then we're going to talk a lot about Bitbake, which is kind of the core. When you think Yocto, just think Bitbake. They're very, very kind of synonymous things. And then Bitbake kind of decomposes into a handful of topics that we're going to talk about: layers, recipes, building and deploying, and then the SDK for your target. We're going to talk a little bit about licensing, which is always like a very touchy subject in Yocto Linux, although the whole motivation of Yocto Linux is to make it less touchy. So you can reliably tell your boss at your day job, hey, we could use Yocto Linux for this embedded system and not have to pay people money for operating systems. So we're going to talk a little bit about how Yocto helps with licensing. We're going to talk a little about support. I can probably skip the Git talk, although it's pretty cool with Yocto if you want to take a moment on that. How many people use Git? Wait, okay, so we can probably skip the Git talk. I gave this presentation, I tried to give it at this mini demo, and I was really frustrated because my new laptop that I'm so happy with only has an HDMI output on it, and they didn't have an HDMI connector at the conference room. It was EGA only, and so I basically couldn't give this presentation. So this is going to be a much better, much more revised version. And then who knows about Qt? Does anybody know about Qt framework? Qt is really, really cool for embedded systems, so we're going to talk about that, and obviously questions. Awesome. So my background, I've been doing embedded systems since I got out of college, which was in 2010, so less than 10 years. And I started at Lasix, and they love those guys at Lasix Industries in White Bear Lake. They have really cool laser systems, and they run embedded Linux for their laser controller. And now I work at Minitronics, which is a medical device company in Minneapolis, St. Paul, where the old Saint Stadium was. And there I do mostly C++, and believe it or not, we're using Yocto Linux on medical devices. So pretty exciting time. So what is Yocto Linux? You guys are all probably familiar with big distributions, Debian, Arch Linux, Ubuntu. It's not a distribution, and the slogan is, part of the slogan is, it builds a custom one for you. And so typically you'll go get Debian or Ubuntu, and then they've basically packaged it up. You get a nice ISO, and it runs on tons of hardware. Yocto Linux, you basically download a tool to configure your own Linux for your embedded target. Now the big motivator for doing that is with distribution, you end up with really a lot of components and a lot of weight that you don't really want in an embedded system. An embedded system is supposed to be very targeted, very application specific. And so the need was basically, hey, we got all this really cool open source software. It can totally run an embedded system. Why on earth would you put Ubuntu on an embedded system? So we need to configure Linux in a very lightweight fashion and put it on an embedded system. And I'm sure you guys have all heard about other distros, smaller distros, like I think there's like a Nano Linux and a Pico Linux. Well, I don't even remember all the names, but there's a bunch of them. And basically Yocto, if you know about scientific notation, is like 10 to the minus 15. So it's a really small Linux, which is kind of why the name's pretty sweet. Sorry?
10 to the minus 24.
It's 24. Boy, it was way off. So that's like really little. Thank you for correcting me. I got to know that. I got to know that. So Yocto's backed by major corporations. It's got a really, really growing community in the embedded space. The documentation is fantastic. It's very, very good. It's better than really any software documentation I think I've really ever seen. It's incredible. The other important point is that when you use Yocto Linux, you have a very highly repeatable build system to get your operating system onto your target. That's very important because when you're trying to configure an embedded device to go to market, you really want to be able to reproduce that in a reliable way 5 years down the road, 10 years down the road, and that's what this Yocto Linux helps you do. It helps manage SoC complexity hugely, and here's why. Modern system on a chip devices like an ARM, we're going to talk about a couple of them, they'll have multiple cores, they'll have network support, they'll have graphics support, they'll have all the standard hardware drivers you normally see, UART and SPI and M2C and PWMs and stuff like that. Except now they're even adding FPGAs, which is what the last talk was about. Either way, it gets really, really complicated really quickly. And the silicon manufacturers basically have to provide you with a ton of software support out of the box because nobody's going to be able to get the IMX6 datasheet out and start writing their own IMX6 UART driver. It's just not going to happen. It's just not even reasonable to do that because that's a solved problem. NPX Semiconductor provides you with that software. And since that software is very generic, it just knows how to talk to the correct registers on an IMX6 and do UART, for example. Then the question is like, well, okay, how do I deliver this to somebody who wants to do UART on an IMX6? And really the best way to do that is with an embedded Linux operating system. IMX6 processors, for example, which is what we're going to talk about today in depth, they're applications processors and communications processors. So they have very good graphics support and they have very good network stack support. They even have wireless and things like that as well, Bluetooth. And so basically the silicon manufacturers have to provide you with some level of support for that stuff because it's not reason, and they just want to sell the hardware, right? So they give you this open source software. And basically, this Yocto project helps you take in those bodies of code in a graceful fashion and get it worked into your target operating system for your embedded system. So it helps manage modern SoC complexity in a very big way. And it also helps with licensing, which is an important point. You know, everybody, open source software, you know, forever, it's just this constant discussion about copyleft and what can I copy, what can I change. And so to help with that in an embedded system, the Yocto project provides you with a really good license manifest and stuff like that. And Yocto Linux is supported on tons and tons of platforms, which is another really exciting thing. So, why would I use Yocto? That's a good question. Because there's other ones. There's BuildRoot. I mean, I know some of the older folks in the audience, they probably have built it with makefiles like the hard way. Like back in the day when, you know, Linux version 0.5 or whatever is out, you'd literally have to go and like get the documentation and like figure out how to make the makefiles run for you. Who's done that?
Slackware?
My goodness. How complicated was that? Did that just take like all weekend and then it didn't even work?
Weekend.
Weekend? Okay, did it take all week and then it didn't even work? Okay, yeah, I can feel your pain because ultimately Linux is massive these days. And even back then it was massive. How on earth does one person go download you know, a million lines of code off the internet back in the day and build it yourself? Well, nowadays, it's like you could go download 14 million, 18 million lines of code off the internet that is the Linux you know, body and put it into something. And if you're just one guy, it's like it's not a feasible task if you're just doing it by hand with makefiles. So Yocto gets around that problem too because it's a very automated build process. So here's some other motivations. So like I said, people have been customizing for years. There's a need to make a uniform solution. Embedded systems are complicated, and microcontrollers are not cutting it as often these days, especially with the advent of IoT. You really just need an operating system. You need to be able to do SSL certificates, and a 32-bit microcontroller falls really, really short on both of those fronts. A lot of times your embedded system needs to do graphics in an easy way, and that's a huge limitation of 32-bit microcontrollers. And so basically there's all these different complicated things that Yocto is going to help you with. You can do just about anything with it. We were able to customize a Yocto build for a project at Minitronics that ended like a year ago. And basically we had a requirement from the customer that said, must be on the touchscreen booted, ready to go within 8 seconds. And it's like, holy cow, have you ever seen Linux boot in 8 seconds? That's a tough call, right? But if you get in your car and you throw your engine on and your backup cam does come up in something like 10 seconds or less, right? So how do they do that? Well, it takes a ton of special sauce. And when you're using car automotive stuff, a lot of times they're using QNX, which can be also very, very customized as a standard thing. And then they'll boot to a camera. They have like a standard mechanism to do that in QNX. But in Linux, it's a little bit harder. You actually need to go in and skip the U-boot, and it's this whole thing called Falcon mode. So I guess the whole point of this statement is you can customize your Linux distro very, very tightly for your exact application. And you don't end up rewriting things that don't exist. Internet connectivity, lots of supported platforms, and it's free. You guys have heard about that though. Okay. This is kind of the fun part. What can Yocto run on? And so I'm going to pass this around while I go through these next slides. This is called a Digi ConnectCore, and I have an entire slide dedicated to it. This is brand new as of like Q4 2016. This is a brand new technology. This big silver guy, this is just a dev kit. It's actually, the product is just this silver guy in the middle with the cap on it. If you look closely, there's a little UFL Wi-Fi connector, so you can hook up a radio antenna. Underneath here, there's a 1 gig of RAM, IMX6, and it's got a support microcontroller to help you do some really cool, clever stuff in terms of security. And so this is kind of like the latest and greatest. This thing can get on the internet and send encrypted data to Azure in like a day if you're using Yocto Linux and you know what you're doing. So we have been experimenting with this at Minitronics, and we've tried all sorts of different system on modules. So why don't we just pass that around? Try not to ESD kill me here? That'd be great. Yeah, at least it's raining out. We're cool. We're good. So, oh man, Raspberry Pi. It'll run on a Raspberry Pi. You guys know about Raspberry Pi. If you're in this room, I think the requirement at the door is that you booted a Raspberry Pi. Okay. So, Raspberry Pi is cool. Normally you'd just get Raspbian or some variant or some, you can put Ubuntu, a lightweight copy of Ubuntu on there. But you can also run Yocto Linux. And if you do that, you can customize exactly which packages your distro ends up having on the target. BeagleBone Black, very similar to the Raspberry Pi. I think they have like even a newer one than this picture I just found out recently from the last time I gave this presentation. Somebody came up, they're like, why'd you put the old one on there? And I was like, this isn't the old one, is it? It is the old one. They have a newer one with better specs now. And you'll notice there's a pattern here. This is a Cortex A8, so it's an ARM. A lot of the embedded stuff is ARM these days because they're just much more effective than most of the Intel offerings. And so that's why Intel's got this ARM problem. Even your phones are running like Snapdragon processors by Qualcomm or TI. Those things are going to be running a very advanced ARM processor because they're just more efficient for power and things like that. And ARM's gone a long way of getting its distribution network to make things like embedded Linux, Yocto Linux, totally easy to run on an ARM processor. Here's the ConnectCore. So it's got SD card. Oh, it's 2 gigs of flash, 1 gig of RAM, 500 megahertz, and it has Wi-Fi and Bluetooth. And what's really interesting about this particular guy is their roadmap for the end of the year. It's going to have, instead of Wi-Fi Bluetooth, it's going to have a cell radio right in there. So you can just skip the nonsense and just put a SIM card in it, or if it's I'm not sure if it's GSM or if it's going to be a CDMA technology, but you'll be able to set up an account on there, and then that thing is just going to boot and just send data to wherever you want via the cell network. And prices for cell data is coming down. They realize that there's just going to be a huge influx of IoT hardware, and so this company, Digi International, which is based in Minnetonka, I believe, or where is it based? Yeah, they see it coming. They were talking about its potential that a cell radio computer chip like this would be a disposable someday. Like you could put it into something that is literally intended to be a disposable. So we're talking less than $8. You can discuss all you want about whether or not that's a good thing, but the prices are coming down really quick.
What's the cost of the board?
That board's $129 on DigiKey. Get it today. Yeah, pretty sweet. All right, so this is a really fun project I talked a lot about in the last talk. This is called a Snickerdoodle, and this runs a Zynq processor. Zynq is by Xilinx, and that's a dual-core ARM, and it has FPGA fabric around it. So this thing's really a Swiss Army knife for embedded systems. You can run screens, you can do arbitrary digital signaling because you have the FPGA. It has Linux. It will boot a touchscreen. And you can have Wi-Fi out of the box with this sort of a platform. So Zynq processors are going to be very popular going forward for embedded systems. You can buy this online for, I think, $100. And they have a bunch of breakout boards for these connectors. You can get the connectors up or down. Yeah, this thing's very impressive. So other platforms. So don't let this fool you. You can run this on a desktop. You could boot a super lightweight Linux on your desktop. And on an i7, Linux comes up pretty quick when you're doing a Yocto Linux. It'll run on AMD. It'll run on most popular target hardware. However, if you do desktop versions of Yocto Linux, you're going to have a bunch more hoops to jump through to get the correct driver support for the more advanced peripherals that your desktop might have. For example, a graphics card is going to be kind of a bear to get put in correctly into Yocto Linux because the graphics driver that comes with an NVIDIA card these days, it's an installer that's like 200 megs. The whole root file system of your Yocto OS could be like 40 megs. And then you got this like NVIDIA driver that's 200 megs. It just doesn't work right. So don't count on a lot of easy graphics with Yocto Linux if you're going to go with the Intel targeted hardware, unless you know for a fact it's like kind of a supported thing. And we're going to talk more about how you figure out whether or not your hardware is supported with Yocto. All right, let's get into the meat and potatoes. You guys want to talk details? Let's get into the details. Okay, this is a really important slide. We'll probably come back to it a couple times. And I hope you can see it okay. This is basically the world of Yocto in a really effective block diagram. So starting from the top, everything in blue is considered Bitbake. That's the build system. And Bitbake is basically a huge stack of Python that these Linux Foundation people put together, and it had basically morphed out of the Open Embedded project. So the Open Embedded project existed to make embedded systems for Linux long before Yocto started. Well, I guess I don't know how long before, but they basically took the Open Embedded concepts and then kind of blew it up into a much larger scoped project. And so Bitbake is kind of like the engine that makes this all happen. It's an incredibly sophisticated build automation tool. So that's the blue area. And then Yocto, the project, kind of consists of Bitbake, but then it also consists of the metadata that makes Bitbake go. Okay, and so the metadata is basically anything that's this kind of dark gray. So that's the metadata and inputs. So at the top there you have source mirrors, and then on the side here we have user configuration. Can you guys read that back there at all?
Yeah.
Okay, cool. Metadata, BB, and patches. So BB are the recipes or layers, Bitbake recipes that we're going to talk about. Machine configuration, BSP, and policy configuration, so like user accounts and things like that. So those feed into the build system, and then when the build system's done compiling, you get a big, huge chunk of package feeds. Now that's really no different than when you do sudo apt-get install on Ubuntu, and you just go pull in minicom, for example. That's what a package feed is, except now these package feeds are going to be on your build system, not on the internet. But the package feeds, which come out of this, in this little arrow, are prepared in an image generation step and an SDK generation step. And the images is what you actually boot your hardware with. It's typically done on a micro SD card these days because it's just really effective. And then the SDK generation is basically when you are trying to, once you have an embedded system, you need to have an SDK so that you can compile software that runs on the embedded system. And so Yocto gives that to you as well. Has anybody ever fought a problem where there are GCCs at one version and their make files know about it, but then some package has some dependency on a different version of GCC, and it's like, son of a bitch, why doesn't this build? It's just a nightmare. So Yocto sanity checks all that stuff for you. It's pretty slick. So coming into the middle here, the build system, the first step it uses is source fetching. So you have all this input data. We're going to talk about the details. And it grabs the correct sources for what you're trying to do, and it patches the sources, and it configures the sources, and then it checks relationships. This block here is incredibly sophisticated. And then it produces your RPMs, DEVs, or IPKs, which are basically the package feeds, and then feeds those out. But the big gray box in the middle there, output analysis for package splitting plus package relationships. This is the magic. This is really, really critical because at any point in time, I could bring in some piece of metadata that says, I really want to build LZOP, or minicom is going to be the example of the day. Except the version of the code that I just brought down was based on the Debian server, and it's expecting GCC this version, and it's dependent on libc this version, and oh, that's not what we have here, and it fails the build. So there's really a lot of very sophisticated checking that's going on there. And I'm not going to sit here and pretend like I know how all that works. I think only Richard Purdy, like the guy who does almost all of these commits to set this whole thing up. And I think he's like the only guy on the planet that actually knows how it works. But maybe I'm wrong about that. But it's a long process to get your head wrapped around how all that works. But anyway, so that's kind of the top workflow. Does anybody have any questions? Does this make sense? Basically, you're going to get this Bitbake build tool. You're going to feed in metadata, and it's going to spit out an image that actually boots your target. And it's already configured all of the drivers and all of the IOs, and you can actually access device tree items and That's
the
the
build
idea.
system itself, the stuff in blue, is that a local, like, is a local VM for you? Or are you
Yep.
building this in the cloud? What are you doing?
Yep, so that's a great question. The build system, typically you're gonna just wanna use the recommended Ubuntu build environment, okay? It can certainly work in other environments. If you wanna go try it on CentOS in the cloud, you know, on your network server, you can go right ahead, but you're gonna have best results if you just do the recommended Ubuntu 14 distribution they're talking about. So right here, I'm actually running Ubuntu 14 because I normally run Ubuntu 16.04 and I couldn't get it to build under 16.04 after trying for like a day. And so I was like, okay, this is stupid. I should have just followed the directions the way they said. Here's the, you want to use Ubuntu 14.04, and then as soon as I did that, it compiled, for example, the SDK, the Yocto project for that ConnectCore product that's coming around built first try. I just hit go. Set up the thing based on the instructions and hit go, and it worked right. So you do want to use an Ubuntu, and so yeah, in this case, it's a local Ubuntu VM. And when you do this, I mean, you got to realize it's going to pull down really a lot of Linux. It doesn't pull down everything. Obviously, there's tons of corners of the internet where you can get special Linux things. But when it pulls down this metadata and it builds all these packages, it ends up consuming about 100 gigs of hard drive space, like right out of the box. So you're going to want to have an Ubuntu VM that with a, you know, a terabyte solid state drive if you can help it, and then you'll be just fine. So that's what I have here. That's what we're doing. Yes.
You said Ubuntu VM. I think maybe you qualified that and I missed it, but it's local, like an EC2 instance or something like that would be not necessarily a good idea, or?
No, if you had an EC2 instance that had Ubuntu 14.04, you're going to be just fine.
Okay.
Yep. It's just got to be Ubuntu 14.04 because that pegs a lot of the versions for a lot of the tools. So like if I do sudo apt-get installed build essential, which is one of the dependencies you need, that's going to pull in a specific version of GCC that is designed for Ubuntu 14. If you're on Ubuntu 16, you're going to get GCC version 6. But Yocto, based on this particular distro version of Yocto, it's expecting GCC like 5.3. And so that's where you start to immediately run into problems, is the packages that Yocto project is dependent on are pegged correctly in 14.04. 16.04 is officially going to be supported like sometime this year. They'll have another release of Yocto, and you'll just be able to use Ubuntu 16. But yeah, you could do it in the cloud. If you didn't want to have a local VM, that's a great way to do it. Just fire it up in an Amazon instance. Stuff's cheap these days. And it'll probably build a lot faster than on my desktop here. All right, so the metadata. And this is really the sauce that goes in. This metadata was those gray boxes. So it's where does the source come from? Which pieces of source am I going to actually build? And how do I get it? So it contains, they're basically set up in recipes. There's two tiers of logic. There's layers. Your system's built up of layers, and a layer contains a list of recipes. And that's basically it. And the recipes are typically individual packages. So if we had a layer called, so what you're looking at here on the graphic, these are all called meta layers. They're layers of data required to build your entire system, and they all follow a naming convention, and they all are categorized kind of based on what the actual macro scope of what is in the layer. So let's talk about what we have here. The top one, meta browser. No idea what that is. I'm just kidding, it's a web browser. It's really obvious. Meta-fsl-arm, who can take a guess? This is what you get if you're going to build your ConnectCore project right now. So who has any idea what an FSL-arm is? What do you think you're talking about there?
Something for ARM?
Yes, and FSL, Freescale, which is now NPX Semiconductor. But don't be confused. The processor on these things is an IMX6. It was made by Freescale. That's what we just showed you in those supported devices. And so when you see FSL, that means that Freescale produced that meta layer for you. And this is what I was talking about earlier. Basically, there's all this configuration and technology required to run these simple drivers, and even graphics. And Freescale's job is to provide you with source code that configures all that correctly for a particular part and deploys that. And so the way Freescale does that is they have Meta-fsl-arm. And that's called a Yocto meta layer, and it's maintained in Freescale's own GitHub accounts, okay? So every single one of these folders, basically, is its own Git repository. And inside that Git repository, you have all of the recipes for that layer. The recipes are being the packages of software that you're going to put together. Does that make sense? So basically, the metadata also tells you how to build the packages and where the RPMs go, or the deb files or the IPKs, the actual output binaries that are going to sit on the root file system. That's all defined in that metadata.
Would it be similar to compare it to a box of hamburger helper, and that's the Git repository, and then the directions are on the box, that's the metadata? So you're getting like, because it sounds like you're saying the metadata and the packages all in one thing.
That's really great question, and it does sound like I'm saying that. Let me clarify, that's not how it works. These pieces of metadata do not contain any source code for the packages themselves. It just contains instructions for Bitbake on how to go get the source and how to compile it and how to package it and how to deploy it, okay? So meta-fsl-arm is only metadata. It does not contain package source code. So let's say fsl-arm had a package. Well, we'll go look at it. There's all sorts of packages in there. But each package is just the metadata for it. It's not the actual source code. Does that answer your question?
Yes, thank you.
Yes. It's a subtle point. I'm glad you asked that. Okay, so this is what Bitbake looks like when it runs. You pull it up in a console. You have to source an environment so that it knows about, I don't know, where everything is. And then once you hit go, it looks through all of those layers that you've defined, and then it says, oh, Andy's got instructions for using this component out of this layer. I better build it. And this is a 4-process executable right here. So it's running on 4 threads. Here you can see Qt base native 5.3.2 R0 is in build step do configure, and it has a process ID number. Linux Verisite, this is the kernel itself, kernel version 3.14.28 R0 is in build step do package. So what is the build step? So when Bitbake goes and looks through the list of layers, it finds all the interested recipes, and then when it needs to build a single recipe, there's like 5 or 6 steps. Technically, you can define n steps, but Bitbake is aware of natively like 5 or 6 core steps that you're only going to be interested in. So do fetch is how it goes to the internet and gets the actual code and pulls it down. So that's the do fetch step. Do I have a do fetch showing on here? I don't. Man, it would have been really cool if I could have like captured it at just the right point to show you a do fetch. So none of these are doing a do fetch. Once it's got the fetch, it has the code, then it says do configure. And configure means extract the packages. A lot of times the fetch call comes as a tar or a zip or whatever, or it's just a clone call of a Git repository. So once you've cloned the code, that's the fetch step, you actually go and you configure, which means extract, and then there's actually another step in there. There can be a list of patches, and so the patches then get applied to your code appropriately. So that's the configure step. And then there's basically do compile, which is obvious. That's what make is called with GCC, or whatever the tool ends up being for that package. And then after that, it's do package, and then I think there's actually a do deploy, which are kind of like the core ones. So this one, Linux Verisite's in the middle of do package, which means that process, that piece of code, is actually getting its RPMs created, in this case, to deploy.
I hope this doesn't confuse anybody, but to me, it sounds like I use Slackware a lot, and it was just a bunch of tarballs. But there's a nice website called Slack Builds where you download the Slack build file, and then you put the tarball in that build, and then the build is like the metadata telling the tarball
How to work, yeah.
how to compile.
Yep.
Yeah, it reminds me a little bit of BSD ports.
Yeah. Yeah, I mean, the workflows for Linux are all kind of similar. Basically, you got it. Well, the workflows for compiling software and deploying software are all kind of similar. You need to go get the source. You need to have a knowledge of how to build the source, and then you have to know how to package it, and then you have to know how to put it somewhere so that somebody can use it. And so that's fundamentally what Bitbake's doing, except Bitbake kind of gives it to you in a very structured manner. All right, next topic. Let me see what I'm doing for time here. All right, cool, it's 10:50. Is everybody cool if I go to like another hour?
Keep going.
Just keep going?
You guys free?
I mean, if I went slower and went into more details, we could do 3. That'd be a marathon. I don't know if my video camera will record that. All right. So now that you have Yocto and you've built your target and it's succeeded, let's say you got completed. Okay, great. Well, actually, one other thing I want to point out in this last step here. Oopsie. You'll notice this line on top, currently running 4 tasks, 2567 of 2600, okay? That means there's 2600 individual packages that need to get built, okay? So there's 2600 URL targets on the internet pulling down these packages, and then I'm building all of them. And what's interesting is you almost never use all the packages. You can specify in the metadata, hey, sure, you can download this package, but you know what? I don't need Minicom on my target. I don't need zip and unzip. Maybe I don't need BusyBox. Although, come on, let's get serious. Everybody needs BusyBox. So that's what that's saying. So the first time you run it, too, it can take like 4 hours. I mean, it took me, I had to start it and I left it overnight. Okay, so once it builds, what do you have? What does Linux fundamentally consist of? Well, this has been an evolving topic. And 10 years ago, this slide might look a bit different. But when we're talking about 2017, we're talking about IMX6 processors and embedded systems. These are kind of the fundamental components I'll talk through. What does it actually give you to boot your target? And this was something that I didn't know about until kind of recently, and I started understanding it a lot better. And it helps to troubleshoot things and understand what's actually happening. So on an IMX6, there's this thing called the primary bootloader, and that's burnt into the chip. And that primary bootloader is a small amount of code so that when the chip comes out of reset, the program counter jumps to that small amount of code and immediately starts executing that. Now that very small amount of code is read-only, and it basically bootstraps the power-up of the chip. The secondary bootloader is typically on an SD card or some other non-volatile memory, or it could be on the chip itself. Kind of depends on the topology. But the secondary bootloader is yet a little bit more functional, except it still doesn't know anything about how to boot Linux typically. But the secondary bootloader gets loaded by the primary bootloader. So the primary bootloader needs to know, and this is where the handoff typically occurs. Have you ever seen a little embedded board where there's a jumper, and you put a jumper between pins 1 and 2, and that means it's going to boot from internal SD storage, or you jumper it to the next one, it's going to boot from SD card, external storage. That's what's happening. Primary bootloader knows how to read the pin and be like, oh, I got to jump over to my EMC subsystem on my IMX6 and go read out of the SD card. On the SD card, in the first 8K, they have this thing called the SPL. And so the SPL is kind of a subcomponent of U-boot. Who knows what U-boot is? Okay, U-boot's been around for a while, and it's like the #1 way that people will use boot Linux, basically. It has support for tons of hardware architectures, and it comes in a kind of a pair, 2-piece thing. It's in the same Git repository. You have U-boot, and then you have SPL. So SPL stands for secondary preloader or secondary bootloader. And it sits at the very first 8K of a SD card. So when the program counter jumps to start reading the SD card's first values into memory so that it can start executing that, that's what it's loading, is this program called the SPL. So then the SPL is a little bit more feature rich, and the SPL can do things like potentially read from a NAND card versus a micro SD card. Or maybe it knows how to, some SPL runs sometimes know about networking, or maybe even I2C. But that's kind of stretching it. Typically, the SPL will just jump immediately to the correct location of U-boot on the micro SD card. That's what we do for the Digi ConnectCore. So then, once it starts running U-boot, program counter's running U-boot now. U-boot is a much more feature-rich, although very small compared to Linux. It does know about a network stack. It knows about GPIO. It can do. You can even do SATA. So that's how you load Linux off of a hard drive on a SATA header. And so it's just a software stack that's a lot more feature-rich, but it's still very low level. And its primary job is to find the DTB device tree binary. Who knows who's heard that term? The device tree binary. Okay, that's how you configure Linux's drivers, like hardware drivers. We'll talk a lot about that a little later. But what it does is it grabs the DTB file and it grabs the kernel image, which is at another address. It's a static address on that SD card, is the entry point of that kernel binary. You guys might have seen it. It's like U image or Z image if it's compressed. That's the kernel. And so that sits on the SD card as well. So the device tree is the way the drivers get configured, and then the kernel is the actual OS. And then the final component is the root file system, and that's typically the rest of the micro SD card. If you have an 8 gig micro SD card, the first megabyte, for example, would be all that other stuff. Well, the kernel is typically like 16, 18 megs. So maybe the first 30 megabytes of the SD card is all this other stuff, but then the root file system starts at some location very shortly after that, and it can take up the rest of the micro SD card. But what U-boot does is it figures out where all those things are, and there's actually a command prompt for U-boot. You can configure U-boot to look at this location instead of that location and stuff like that. And U-boot will gather up those three things, and then it calls init on the kernel, which is the entry point to the kernel. And when you launch the kernel, you pass it a couple of arguments. First argument is where is my device tree binary. Second argument is where is the kernel image itself. And then the third argument are what are the command line init arguments. Has anybody ever had to play around with like X and then they had to go change their command line arguments for the launch of the Linux kernel? That's what U-boot is trying to provide to the kernel. Any questions? Good? You guys learning something?
Oh, yeah.
All right, cool. All right, and then the root file system. Okay, so that's basically what ends up on your micro SD card once Yocto is built. So, at this point, I was going to sit down and we were going to walk through a setup of a Yocto build for the Digi ConnectCore. And since it takes like 4 hours to build, I've already done that part of it, but we were just going to basically show you how it gets set up pretty simply by some simple directions, and then hit build and just show you what Bitbake looks like. And then the next slide, I'm going to talk about some useful Bitbake commands. That's kind of a busy slide, but we'll get to that. And then we'll talk a little bit about kernel configuration and how to deploy it. Cool. So I'm going to sit down.
This must be worth it hard.
Well, no, this is where we get to use the like 32 massive font in my terminal here to show you how this actually works. So I'm under Ubuntu GNOME 14.04 here, and we're going to be looking at this screen, which is my folder browser. Can everybody read that okay? We're going to be looking at this screen, which is the command prompt, which is where we're going to run Bitbake. And then we're going to be looking at this screen, which is the directions. So if you go find the setup guide for the ConnectCore, and then you manage to forget to connect to the internet, and then you can't get at the directions. One moment. Major fail.
Work you back up to the wireless, or?
I was on it, and then I got
You booted.
too fancy. And really interesting. I wanted to install Minicom on Ubuntu just now. You saw it before anybody got here. Except I was on the Veritas Wi-Fi, and turns out Veritas uses a lot of Linux stuff, which is why we're here, right? And interestingly, I tried to do sudo apt-get install Minicom, and it couldn't find the repositories. And who works for Veritas? You work for Veritas.
I do.
Is that because you guys block accidental access to those types of repositories so you can control better where that... Well, it didn't work, needless to say. And then I went on my cell phone Wi-Fi, and then that did work. And that's really interesting to me. So we'll go back, oopsie, see if I can get right back on Veritas Guest here. One moment. I already authenticated. Yeah, all right, Veritas. So this should work. Let's refresh this. So Digi's documentation is actually super good, and kind of wish I had downloaded the PDF of this first and be a little more prepared. One moment. The CNN litmus test. Oh, that works. So let's just, anybody know where Firefox keeps its refresh button?
It's that F5 button up there.
No. Navigate again. CNN worked.
Gigi's
Gigi's
Nobody's
just
developing it.
trying to screw up my.
Is it up or is it just me.com? Have you been to that site?
Oh, is it just me? Yeah.
Yeah.
Check it out.
Check Digi.com.
You know, we don't even necessarily need that. Well, we can.
The demo gods.
Demo gods love this. Well, what the heck?
There's smiting bee.
Okay, we're going to try Wi-Fi 2. One moment. This will just be a quick aside here. We do want the directions.
They're trying to show them.
No way, the Digi site's down. Give me a break. Yeah.
There you go.
So Veritas's internet is throwing curveballs at me. It's okay though. And we're in. So check out this super good documentation. Fancy. So basically, you can talk. They show you about the hardware. They show you about additional resources, and then you click this Yocto button. And well, let's do the getting started. Well, what are the requirements? Well, oh man, I'm going to need hardware, obviously, and then system development. Okay, so they start off with FTP setup because what they want you to do, a very common workflow, is when you're trying to change the kernel a lot, you're changing the root file system a lot, it's super cumbersome to always have to keep burning images onto SD cards every time you want to boot a new image. So what they let you do is they let you install TFTP, which is a daemon that lives in Linux, and it lets you network boot. We're going to skip that step because we're just not going to do that today. So then they say, well, let's install Digi embedded Yocto. So the first step is to pull this curl, make a curl call, and it's going to go to google.com, and it's going to pull in this thing called the repo tool. And the repo tool is pretty commonly used with Linux because, like I showed you before, that one slide with all the meta layers, each one of those meta layers is its own Git repo. And so this repo tool helps you create a manifest for which repos you're actually interested in, and then deploy that onto your system. So first step is to install the repo tool. I'm going to skip this because I've already done it. And then when you install the repo tool, you have to set up a folder for what you're going to do with it, and then you're going to change into that folder. So here they're talking about user local DEY 2.0. I like to operate out of a different folder called opt. Who likes opt? What's your, okay, let's have a poll. What's your favorite? Raise your hand if opt is your favorite root file system folder. Okay, raise your hand if it's user though. Come on.
So you might as well ask if
Put it in
people come from AT&T or BS. I mean,
Okay, okay. Who likes the home directory?
Yeah, I like home.
All right, all right. This is a very polarizing topic. I've been working on opt lately.
I like Dev Null.
Sorry? Wait, what is it?
Dev Null.
Yeah.
The dark side of the moon.
It's funny. It's really funny. All right. So I have a ConnectCore folder here. Can anybody see my head in the way of that? No, good. So in the ConnectCore folder, there's two folders. There's the CC IMX6 UL. So the actual target is called an IMX6 Ultralight. It's the lower power version. They have a lot, so it's like 500 megahertz, and it consumes only a handful of watts. They have a IMX6 Quad, which is like a quad-core gigahertz model, and that thing is a lot more heavy duty. So the Ultralight has all the same compute functions. It just isn't quite as fast, and so that's what we're targeting here. And then DEY stands for Digi Embedded Yocto. And so basically, whenever you set up your folders, you're going to end up with, fundamentally, you're going to end up with these two components. The CC IMX6 folder is where all of the work actually gets compiled and actually downloaded to. So when the source gets, the metadata comes down, the metadata lives under DEY 2.0, and then the actual build area where the whole system is actually, where Bitbake is run out of, that's under the CC IMX6 UL folder. Okay?
You need the 100 gigs.
Yeah, that's where you need the 100 gigs. Yep. So the DEY folder is just the source's metadata, and that's only a couple, dozen meg. It's not that much. But then the CC IMX6 is where you're going to be ripping through 100 gigs the first time you build it. So if we change directory into the DEY folder, there is a makeproject.sh and a sources. And so makeproject.sh is a pretty important script that Digi gives you when you clone. And so let's go back to the instructions, and I'll just show you which step that's at. So here we've done a repo init. They told me to go into this DEY folder in the last step, and then they said, let's do a repo init using the this github.com manifest file, okay? And then we're going to point at branch Jethro. So if you look, so Yocto's got a succession of named releases, and Jethro is 3 releases ago, and the more recent one is Krogoth, that's mid-2016. Morty just came out, that's the beginning of 2017. And so typically these embedded devices, they're going to be like 2 or 3 levels behind the latest. And so right now, Digi releases the Yocto project pointing at the Jethro branch, and that's the version that you're going to use. So then you call repo sync, and then that's going to download all of the code based on this manifest file. And again, the code I'm talking about, this is the sources, this is the metadata that it's going to download. And it's going to download the actual Bitbake Python stack to do this. So once you've called repo sync like that, you're going to end up with this folder. Maybe we'll get off the command line and go to here. You're going to end up with DEY 2.0. And then in here, you're going to have a script and a sources folder. If we go into the sources folder, here's your metadata layers. That looks a lot like the image I showed you earlier. So Pokey is the core metadata for like common Linux things, including compiler tools and make and stuff like that. Meta Software Update is a repo that Digi designed to make it easy for you to do wireless over-the-air firmware updates of your Linux OS. That's pretty slick, so there's a lot of tech there in the Meta Software Update. Meta Qt5 is the entire Qt framework. So if you want to run the Qt framework on your target, which we'll talk about a little later, that's how you're going to pull that in with Meta Qt5. Meta Open Embedded is further pieces of a core Linux system. FSL Demos is just demonstration code from Freescale, probably not required. FSL-ARM is going to be the actual core driver level configuration of your target and all of the Freescale provided metadata. And then Meta-Digi is actually kind of the core product release layers that go on to the BSPs basically for that exact prototype kit. Now, it's kind of a lot to know here, but basically when Bitbake builds, it looks at all these layers and then it finds all the recipes, and then recipes have individual names. And what's interesting about the way Bitbake works, it's kind of like an onion. You can append actions onto recipes kind of indefinitely. And recipes have what's called a build priority. So let's say there was a particular package in Qt5. Say I was using Q serial port, and let's say I found a bug in it. I could make my own meta layer, call it meta-andy, and then I can put an append file, and I can override the behavior of the serial port in Qt. So that's how basically Bitbake, it's like an onion. It builds up all this metadata, and then it parses through it, and it knows whose priorities are over whose, and it runs your stuff last. And then you can then tweak things exactly how you want it. And so that's kind of how it works. I'm going to make my own meta layer that takes all of these other metadata layers, and it just tweaks them after the fact to give me what I want. All right. So if we go back up to DEY 2.0, this make project is a really important script that you only call one time when you first download it. So we go back to the instructions. They'll say, okay, so now you're all set up. Let's create and build a project. So in here, they're going to say, hey, if you call source on this make project script with an L, it's going to list targets. In fact, it'd be kind of a fun one to try. Oopsie.
Because they use user.
Yeah, thank you. I'll get there, Trust me, I've done this before. Yeah, why didn't he follow the directions? That's actually a good point. So this list function tells me, hey, this Yocto instance knows how to target the IMX6 starter kit, or the single board computer, which is a lot bigger IMX6 product, or this other bigger, even still, IMX6, not the ultralight but the full-size quad IMX6 single-board computer. And so this is all stuff that was brought in by Digi International repos. Okay, so when you call this script, it's going to set up the build environment variables that you need on your target. And what that ends up doing is it sticks a. This step's very important. Let's go down and see where they're talking about this. So I'm going to call this eventually, and I'm going to point. I'm going to say I'm going to choose with a P. I want to shoot the starter kit. Okay. And then what that gives you is this bblayers.conf and this local.conf. And then the question is, well, where are those? Let's go back to the folder browser. I'm going to just kind of scramble your brains here. We're going to switch off. So when you call that script, it's going to create for you in this CC-IMX6 UL starter folder. Again, this is where the actual building and compiling is going to take place. It's going to give you a temp, a state cache, downloads, and then a very important script, DEY setup environment, and conf cache, and a lock file. And we're going to talk about what each of these are. But first, we'll go into the comp folder. And this is the bblayers.conf file. And so this tells Bitbake, okay, here's the metadata layers you're going to parse when you run. So if I open that with gedit, you'll see that it's got populated with my correct folder because that's what that script does. It points at, hey, we're going to use meta, we're going to use meta Yocto, we're going to use this open embedded stuff, we're going to bring in Qt5, we're going to bring in these Digi meta layers, and then that's basically this environment variable, bblayers. So now, this is a comp file. There's basically 3 categories of files that you got to care about. A comp file, and there's only 2, and we're going to show you both of them. This bblayers file, or there's 3. This bblayers file is the macro view for Bitbake. Which layers am I actually going to include? So if I made my own meta layer to customize things, I would add it to this list, and then Bitbake will parse it and try to find recipes. So that's the first configuration file. Second configuration file is the local.conf. And if you guys are familiar with like building code from Eclipse or from Qt Creator or whatever, a lot of times when you build code, they'll have, or even Visual Studio, they'll have a .user file that sits locally, and that contains user-centric configuration for a particular environment. You can think of that like the .local file that I'm going to show you in a second. In fact, let's pull up the .local file. The .local file sits right next to the bblayers file in the local.conf folder. And it has all sorts of configuration for the build. And you can even keep track of what version this is with this little variable, and that pops up in Bitbake. So we can do things like accept EULAs. Okay, this is a pretty long file. I'm already at the bottom. Let's go back to the top. We can do things like selecting machines. And a machine is an environment variable that guides a lot of the build process. In this case, we have a machine configured called CC-IMX6 UL starter. And again, I didn't make this file. That script that we were just talking about produces this file. And the defaults are all good. Use Digi International's Git repositories, where to place the downloads, where to place the state cache, which I'll show you in a minute what that is. And so basically this is all just configuration for your local build. And the defaults are all good out of the box. And you can do things like, here's a nice one, extra image features is a keyword. And we're going to turn on debug tweaks. And so this local.conf file can be used to tweak your build with these keywords. And I'm not going to dive too deeply into all of the keywords because that's like a long manual. You can check out. Anytime you see these capital words with underscores, that's a Bitbake-centric variable. And when you start Bitbake, you are going to be adding or removing content from these Bitbake-centric variables. There's a handful of important ones, and that's what's going to basically tell Bitbake what to do with specific changes. So like, if I turned on extra image features, tool Eclipse debug, add Eclipse remote debugging support. So there you go. Man, if I wanted to use Eclipse for my IDE on my environment, my host environment, I'm going to probably want to turn on Eclipse debug so that I can get the TFC agent. Anybody use TFC agent? Runs on your target, and then that's how you can remote debug sessions on your target. Debug tweaks gives you GDB. And so if you have a GDB-based workflow, debug tweaks already gives you that. In a production run, when you're building this for an actual deployment in the real world, you would obviously turn off debug tweaks because you don't want to have the root password to be root, stuff like that. All right, so we could go through this all day, but basically you just need to know there's a local.conf and then there's a bblayers.conf, and those sit under the conf folder of the actual compile area. So the other thing the script makes is a setup environment script, and this sets up all of the terminal's environment variables that are required to make Bitbake run correctly, and we have to source this before we actually run Bitbake. The downloads folder is where all of the actual package repositories get put before they get extracted and compiled. And so the downloads folder ends up being really big and a lot of data, but it's all compressed typically. So you'll see this is 1,593 items currently. It looks like it's a couple gigs. And when I go in here, every single one of these is going to be patches and .done files, and then you'll get into bigger items that are actual folders full of code. So like here's QEMU. Who knows what QEMU is? It's a simulator. It's a Linux simulator. Great. I love it. There's a ton of hands through up there. Okay, so here's the Python 2.7 tar file. So if you want all of Python 2.7.9, lives in this tar file. So if you go back here, you got the downloads folder, you got the conf folder. Don't worry about the cache folder. We're not even going to talk about it. The state cache is an important folder. So as Bitbake's running, it keeps track of its progress very, very closely. It knows exactly which steps it's in for all of the packages, and that's maintained in this state cache folder. So for example, let's say I told you the first time you run this, you get 100 gigs of downloads, and it takes 4 hours. Let's say your computer crashed in the middle of that. Well, historically, that can be a disaster. You might have to start over. But because Bitbake maintains the state cache folder, you will always be able to just pick up right where you left off. It's actually super effective. So if I killed the build halfway in, it knows all these packages got done, and it knows it's got 2,200 other packages to go, and it'll maintain that for you. So then the temp folder is where the actual compilation occurs. And the temp folder is fundamentally the one that ends up blowing up to being like 100 gigs or 90 gigs. So if you go into the temp folder, we'll get there in a second, but first we're going to do a little bit of Bitbake calls here just to show you what's going on. So if I go back to my terminal, I told you I can go back to the directions. I told you I can call source here on this make project, and I do that one time, and it's going to set up that folder with the BB layers and the local.conf, and it's going to set up your environment for building. Once you've done that, you basically have to source the environment with this setup script, and then you basically call bitbake core image base. And now core image base is a recipe, and it contains a very top level tree of dependencies that need to get built for you to create an image that will actually boot your target. And again, core image base is an arbitrary name that Digi International configured. You can make an image called, my image, and then you can specify exactly what gets built into that. So as an example, they give you core image base out of the box, and that's going to get you booted on that Digi board that I showed you, and it's going to be like something like 80 gigs for the whole root file system, which is just really lightweight. It's really cool. So to do that, let's go back to the, sorry?
80 gigs or 80 meg?
80 meg. Yeah, 80 meg. Yeah, and if you want to get really heinous, you can just keep stripping stuff out and making it smaller. On a bigger distro, like on this Dart processor here by Verisite, the root file system, because I built in X11, ends up being like 700 megs. But you can take packages out from there if you'd like. So if I'm in my DEY 2.0 folder, I'm going to go up a folder to the actual build area, which is going to be the CC folder. And then I'm going to call source. What the heck is the name of that file?
Was that Digi website, like the wiki pretty much?
It's the documentation for that actual product. Yeah, and it's like a nice, you can print a whole PDF of this entire document. This document's actually kind of crazy. Who knows what like secure boot is? You ever heard of secure boot? Well, if you're trying to do an IoT device and you're trying to, for example, I don't know, send HIPAA compliant encrypted data up to an encrypted Azure store, you're really going to want to make sure that your target in the field doesn't get compromised. And a really good way to do that, IMX6 has support for Linux Secure Boot, which is a project that has been around for a while, and it uses hard encryption technology to actually secure boot your OS, so that the only image that the hardware will boot is a digitally signed encrypted image. And then your root file system is encrypted too, so that if you store patient customer data on there, you can be sure that there's no possible way to get that data out. And it's crazy, if you actually go down to this trust fence, this is a feature set of this board. You go into Secure Boot and they start showing you these awesome graphics. This is a worthwhile read just because the graphics are so awesome. Look at this.
You know, I think you can just encrypt your whole file system
Yep.
before you install your operating system.
Absolutely. Yeah, and that's like the Ubuntu easy way to do it, but there's workarounds for that. And then if you read this documentation, you'll learn that there's a lot bigger picture going on. They'll talk about how to actually, these graphics are so awesome. Just walks you through. I mean, it took me like a half hour to read this, and now I feel like I know more about Secure Boot than I've ever understood in the past. It's pretty crazy. So this is a worthwhile read too. They just walk you right through how the keys are actually maintained and stuff like that. That's under the trust fence section of the Yocto documentation for this board. Going back to the instructions for running here, we got down to the bottom here, and basically we're about to call Bitbake core image base. And I kind of got distracted. What were we talking about there?
Source name of the file.
Yeah, thank you. Great. So the name of the file is DEY setup environment. So we're going to source this. And then it tells you, hey, now you can run Bitbake, and you can point at a target. So if I were to do Bitbake core image base, Bitbake's going to spin up, and it parses it loads the cache, it resolves dependencies, it pulls up the task queue. Watch, I'm going to get an error first try. Yeah, just like, come on. So it gives you a bit of information about your metadata layers that you're pulling in, and actually what Git version they're at, which is kind of cool. Tells you about your target hardware. Target floating point unit is VPF Neon. And again, this is all set up by Digi. If you had to do this yourself, it'd be complicated, but Digi's handing you this out of the box.
So that 4 hours that you're talking about, the first build, is it going and grabbing the GCC compiler? Because I see the tune features in target FPU.
Yeah.
Is it going and grabbing the native cross compiler
Yes.
to come with Ubuntu, or is it building a brand new version of GCC?
It is going yes to both of those.
It's doing both.
Yeah, it's crazy. So to build code for your target from Ubuntu, the target's an ARM A7, okay? And so that's a specific instruction set. An Intel Ubuntu instance is a totally different instruction set. So you actually got to download from the internet the appropriate cross-compiler that runs on Ubuntu, and then it builds that cross-compiler so that you can then use it from Eclipse and build code for your target. The other thing it does is when it builds that cross-compiler, it bakes in the actual knowledge about which libraries you have and which ones you don't have. So for example, say I was building and I wanted to compile against glibc, but wait a minute, my Yocto image hasn't defined glibc. It actually takes care of all that for you. So it's pretty cool. But yeah, that's a really good spot. So it's going to do a lot of stuff. And so right now it says task summary, attempted 4,162 tasks, of which 4,162 didn't need to be rerun and all succeeded. Super verbose. And so, well, basically that's because I ran it yesterday and it succeeded. So Bitbake with that S-state cache keeps track of what worked and what didn't work. So let's say I wanted to clean a package and rebuild it. So there's all these Bitbake commands that you can be aware of. And I'm going to go back to my slideshow and we're going to talk through. So right now we've talked through the local.conf, we've talked through the bblayers.conf, and there's a layer.conf, which I should talk about real quick before we go further. Each of these layers in the metadata, under DEY2, sources, here's the metadata. Every one of these layers has its own conf file. And that's just how it works. So if I go into the FSL-ARM, or Meta-Digi rather, and I look in here, Meta-Digi-ARM, there's going to be a conf folder, okay, for this particular layer, and in this particular conf folder there's a layer.conf. So if we open that up, you're going to see more Bitbake centric configuration stuff. And again, this is provided to you, so you don't necessarily need to change this. But the point is, every single layer has its own conf and its specific configuration for that layer. And when you see this kind of syntax, kind of like this plus equals, a couple environment variables, BB files are the actual recipes themselves. So minicom or glibc, they're going to have their own minicom.bb file. And then if you want to append or change things after the fact, you use a .bb append file. And so this is saying, hey, in this layer, these are the BB files. We're going to look in the layer directory, and we're going to look in the recipes folder, and we're going to * search and grab all of the all the BB files. So if we went back up to the folder, where'd that folder go? Oh, it was on top of this. So I close this. We went back to in here. Here's the recipes BSP. Let's go in there. Oh, ALSA state. Who knows what ALSA is? You guys got that. The audio subsystem, right? Everything in Linux audio loves ALSA state. So, you know, that IMX6 has an audio output pin on it. You can hook it right up to a little op amp and play music. And so that's going to come from this ALSA state thing. And so look at where we're at here. We're in Meta-Digi. So Digi is customized ALSA state, but you'll notice it's a .bb append file, which is because Freescale gave you the original version, because the IMX6 hardware audio codecs are configured by Freescale, but then Digi says, oh, we're going to append that configuration, we're going to make more changes to it. And so that's what this ALSA state.bb append file is, because somewhere else in the fsl-arm folder, there's an ALSA state.bb file, and that's the original definition of the recipe. And so here we're appending it. So if we look at this, it's going to bring in some source files, some URI files, so it's bringing in some state files here. I don't know what state files are like the audio levels in the ALSA mixer. And then if you look further, there's probably going to be some patches. It looks like it's just state files. So it's just setting the volume controls, basically, and the microphone input and stuff like that. So that's what Digi added on to that specific recipe. So what if we looked at another one? U-boot's going to be a little bit too complicated. Firmware Atheros. So why do you think firmware Atheros is in the Digi meta layer? Anybody? Any thoughts? Any hypotheses?
Wireless.
There you go. Atheros is a wireless chipset. So the nice thing is, anytime you see these terms, I mean, you can just Google them and figure out what the heck they're talking about. So this is going to be the firmware configuration for the Atheros chipset that's sitting next to the IMX6, so that this thing can get on Wi-Fi and have Bluetooth. So if we went in here, we'd have a firmware atheros.bb, and you could see how that's set up. And then these folders that sit right next to the BB files contain source files and custom patches and stuff like that. So a lot of times you'll see an actual .patch file, or you'll see this bin is probably some sort of firmware binary. I mean, this stuff gets pretty complicated pretty quick, but the important thing is they've set this up for you. So that's kind of what the topology looks like. Going back up the tree here, you go back to sources, and that's all just under the Meta-Digi layer. You know, we can append our own layer and make even further changes to those if we wanted to. And so that comp file, getting back to the original point, is under each layer has its own layer.conf. And so when Bitbake goes into a layer and it's going to build all this stuff, there's a comp for that layer. So if we go back to the slideshow, those are the 3 comp files. And that's like, whoa, and that's like all you really need to know about it. You're not going to change the layer.conf files unless you're making your own layer, in which case you're going to read the manual and learn how you do a layer.conf file. BB layers is a really simple one that just tells you which meta layers you're actually going to use. And then local.conf is build specific settings for your local VM. And there's tons of documentation even in the local.conf file showing you what you're actually interested in. So we just kind of talked about base meta layers plus target meta layers. So the base meta layers are like I talked about earlier with the ALSA example. Freescale gives you the base.bb file, and that's going to compile and it's going to work. But because Digi wants to set the mic gain and stuff like that, they do a BB append to that layer, and then those rules get baked in after the fact. So let's go back to Bitbake now, and let's show you a couple things on Bitbake. So like, what if I did Bitbake with a C command, which is a specific command, and there's a handful. You can go look at the Bitbake documentation. There's all these switches that you can use. C is a very common one. And we're going to say clean all. and we're going to say ALSA, one sec, let's just get the name of that BB file quick, in a moment. So the one we were just looking at was under the sources, under Digi, and the Digi ARM, and there was a BSP, and then there's ALSA. So ALSA-state is the name of a recipe. So let's clean that recipe. So here, first I'm going to spell it wrong. ALSA-stat. Stop. So it's going to check the cache, and it's going to say nothing provides ALSA-stop. Well, that's because none of your layers have a recipe called ALSA-stop. And it's even so good as to say, you know what, but there's an ALSA-state. Maybe that's what you're interested in. No, go figure. That is what I was trying to do. So that's pretty sweet. ALSA-state. So we're going to clean ALSA-state. And so now, historically, you'd have to go navigate to the folder, get to the make file, or the autocomp file, and then call clean. And that would take you forever, but you can do it all from Bitbake. You can just point at a recipe and call clean on it. And then if I were to do this again, I can build, instead of building an entire image, which is that core image base keyword, that's the name of the whole system image, I could build just ALSA-state. So let's do that. So look, it's looking through, see how there's 735 packages? That's the dependency tree to build ALSA. That's crazy. You can literally see it happening here. So it said 735 tasks, of which 722 didn't need to be rerun because those packages already were already built correctly, and all succeeded. So we just managed to re-extract the source code, patch it, compile it, package it, and now we're ready to go with the ALSA package. Is that pretty cool? It's pretty cool. That's awesome. So let's go through a couple more of these Bitbake flags, and you'll learn a lot more about how Bitbake actually works. So we've talked about recipes and packages. Kernel configuration is cool. We'll show you that in a second. And then the results, and then the deploy. So if we go back here, there's one more slide. So here's a set of Bitbake commands that are super useful. We'll go through a couple of these. So the one I just did was Bitbake package C task. So one of the tasks available for each package, like I said, there's a set of 5-ish, is a clean. And a configure, or a do fetch, you can force those tasks to run with the C switch. C dev shell gets you a command line call that basically gets you into a shell in the environment for that package. So if you wanted to call make yourself, or do some configuration, you can do that. Package C list tasks is pretty useful. Let's do that one. So Bitbake -C, I'm already forgotten. -C list tasks, and then also state. So it's going to tell me which tasks exist in terms of build steps for ALSA-state. And let's see what this outputs. There you go. Well, it turns out there's actually quite a few more steps. I narrowed it down to the simple ones. There's check URI, there's clean, there's compile. So you could execute any of these individually. So that's a nice way to check out what steps are involved in actually building a specific package. Here's a fun one. Kernel recipe name. This is going to really hit the heartstrings of you folks that have done this by hand in the past. You can do kernel recipe name -C menu config. Watch this. Remember how hard it is to get the damn menu config to work right? Oh, I just want to turn on the menu config. Okay. Bitbake. -C menu config. And I think the name of the package that actually provides the kernel in this case is called, and I haven't done this yet, so I might be wrong, Linux-BEY. And if I'm wrong, it might tell me how a close one. Oh, BEY, DEY. Man, I was close. Son of a gun. DEY.
You got a little millennial there when in the day. So.
Yeah, it had Bay. Linux Bay. So that's the name of the kernel package to actually go get the Linux 4.1 kernel off the internet and build it. And so right now we're doing a cross ARM step, do compile. This might take a moment, but we're going to let it go. And then it's going to pop up the menu config, which if you're younger, maybe you've never even seen the menu config, but this is like the actual UI you can use to configure the kernel. You want to turn off USB drivers, just turn them off. You want to turn on Wi-Fi, go in there. You want to make it so that you can't plug in an HID keyboard, go into the menu config, and Linux has a switch for that. It turns out if you actually go and spend some time looking through the menu config for Linux, you're going to learn a lot. There's a lot to learn about what Linux can and can't do and what drivers exist and things like that.
File system support, so your root system is red when you want to boot in it?
Yep. You could turn on it RAMFS. You can turn on, I mean, there's just so many switches. It's crazy. You can turn on specific drivers for Freescale. So like there's a VPU Neon hardware floating point accelerator in an IMX6. So if you go look at the menu config, you can go dive down into drivers and find where Freescale has actually put configuration settings into the Linux menu config so you can turn on the hardware floating point or turn it off if you'd like.
Do you usually just Google that to find out like where, like which menu config items you need to?
Absolutely. There's a little bit of help info for each option in the menu config, but 9 out of 10 times you don't know what they're talking about. You just go Google it.
Google it?
Yeah. So I kind of wish I would have run this before coming here. It might take a couple minutes. We'll see. So going back to this. So that's how we're going to pull up the menu config. We can call Bitbake show layers. That'll show me which layers Bitbake's aware of. You can show recipes. You can search through the recipes. Like star image star is going to only show me recipes that produce an output image that can actually boot the target. We can print environment variables for a single package. We can clean. I showed you that one. We can turn on verbose output. And let me tell you, it's really verbose. It's crazy verbose. Bitbake will just start yelling at you on all the details if you want to dive in that hard. And then the last one I want to show you before we go back to the further slides is this really cool one called GU dep export. And what that does is it actually gives you a dependency walker for a package. So a lot of times if a package fails to build, it'll tell you, oh, I failed to build because this other piece of software is not at the right version or something like that. So you can call the package, you can call the dependency walker on that specific package, and then you can say, oh look, also state is dependent on glibc, or maybe it's not. But you can also do what's called a reverse depends. So you can see which other packages depend on also state. Pretty powerful. Ton of math. Oh, son of a gun, do compile. You know, it's funny, I should.
I was going to ask you, for the processors and boards that you've been building for, how much customization are you having?
A lot. We do a lot of customization.
Yeah, so you're actually dorking around with the menu config quite a bit.
Oh yeah. Yeah.
I mean, for the average experimenter who might.
You don't need to.
Yeah, it's pretty, it's built as much as you can for that particular process.
Yes.
Okay.
Yep. So when you do the Digi ConnectCore workflow that I just showed you from the instructions, the menu config settings are going to work perfectly. It's going to have all the hardware features of the IMX6 turned on correctly for you. Yep. So I don't know how long this is going to take. It's kind of unfortunate. I am recording the screen. Oh, do install. Yay! Okay, so now we're on to the do install steps. This is going to be shorter. It's just basically got to package everything up, do populate sysroot. So that step is where they actually put it into the final image that you boot your board from. When I haven't shown you this yet, but when Bitbake completes, you literally have like SD card images that you can literally copy onto an SD card and it'll just boot your hardware. Hey, there's menu config. So this is something that you used to have to do from the command line, and it is complicated. Hey, there we go, menu config. Man, now we're partying. Oh man, we should have a whole presentation on menu config. So in here, you can say, okay, well, I want floating point emulation. There's my VFP floating point maths. It's funny that they use the word maths there. So yeah, you can go through here. You can power into any one of these things and just play around with it.
You can shoot me now, but like I've always added like everything. I'm like, I want to compile all of it, and then I find out the kernel doesn't like that. It's like I added one option or one file system that it didn't like, and it didn't compile.
Yep.
That's where I would want to see some reverse dependency error verbosity. That's
Yeah.
like, what did I select that's making this damn kernel not?
Yeah. Bitbake's going to help you with that a lot because when Bitbake fails, and I'll show you what that looks like.
Really? It'll show what kernel option that I
No, it's not going to tell you how the kernel dependency goofed it up, unfortunately.
Okay.
That's just, you just need to be a guru to understand how Linux software stacks work. But what's nice though is it makes it simple. Well, now hold on.
Bang.
I don't have a good answer for that, but the workflow can be a little simpler, and here's why.
Okay.
Say I changed a menu config option. I can go back to the command line on Bitbake and do bitbake clean Linux DEY, and it'll clean the kernel. And then I can just do bitbake compile, and it'll rebuild the kernel. And if it fails, you'll know, oh, I just changed one switch. Now it doesn't build. Now I know what happened. So typically when you're doing kernel menu configs, change one thing, recompile. Find out that it worked right. Change another thing, recompile. Device drivers has entire, there's so, I mean this, I almost want like an art piece that's like the size of a wall showing this tree of options blown out into a, man, it'd be really cool. Yeah, that does. So anyway, yeah,
You
there's
just
just,
print the config text, the kernel config text, and that's what it is.
yeah. So this, the kernel menu config is a little bit outside the scope of the talk, but it ends up creating a .config file, and that's a flat text file that has all the switches and what is set.
You know, that'd be a good example.
Yep, so you can print that. Yep. We actually version control it. So the metadata that we produce, you can stick that in Subversion. Super useful because, or Git, because then when you change the kernel config, that .config file changes, and then you're like, oh, I turned this switch on and my hardware doesn't boot anymore. Okay, revert the .config file, and you don't have to remember how you changed it in the menu config. You just source control it. It's a lot easier to just keep track of what happened. And then here's the really cool dependency walker. Let's try this. Bitbake image GU export.
What would be the source config like? What that? I'm not too sure. I guess I'm not.
No, what's your question?
The last thing you said, I didn't quite catch that one.
Okay, so we're going to do this command right here called, on the second from the bottom, bitbake. Oh, that whole, the part about version controlling?
Yeah.
Yeah, I don't think I heard about that.
Yeah, no, it's a good point to understand. I'll hit it real quick. When you do this, what you end up doing, like the professional workflow, is if you go up to these metadatas, you'll notice there's a meta-digi. Well, that's all of the new recipes Digi made to customize the Yocto Linux for that board. But if you had your own, say I took that IMX6 and I put it on my own printed circuit board, I might have pinouts that are a little different. I might need to change some things. And so what I would do is make a meta my project, okay? And that then contains metadata for your particular target. And in that metadata, you would contain that .config kernel config file. So then what you do is you commit everything that's in your custom meta layer into Git, so that if you're changing things and then you break your build, you can go look at Git and see which files have changed and how they've changed, and you can just revert them. It makes it so you have a safety net. And then as you configure more stuff and it works right, you test it, you commit that metadata into your Git server for that meta layer.
That's like the point of an embedded system.
Yeah, that's how. That's literally like the recommended approach.
I'm familiar with like an ARM architecture. You're looking for like using a cross compiler. You just kind of cross compile the kernel, and you just mess with the kernel and stuff to get all your hardware working and stuff.
Yep. So that's exactly what we're doing here. When you fire up menu config and you change things, Bitbake's gonna rebuild the kernel with those changes.
Okay.
And it's really streamlined because I can just hit compile core image base. It'll detect that the kernel config changed. It'll rebuild the kernel, and it'll produce a new SD card image for you. It's totally streamlined. Yeah. All right. So, also state GU dep exp. This is really cool. I was blown away when I saw this the first time. Wow. Just pulls up this is written in Python actually, it's pretty slick. It comes with Bitbake. And now I have a massive tree showing the dependencies of a particular, this might actually have done that. I corrected it. I'm corrected. This is all the packages. No. I think this is just for this device. So if I click also utils, So also state's the one I ran. At runtime, it depends on state dev, also states, also utils, also CTL. Those are other packages. And then for other people to build, this is what's called the reverse depends down here. There are no reverse depends. But what if I clicked a different package, like something a little bit more low level? Find a good one, glib 2.0. Okay, well glib 2.0 has a reverse depends of udev. So, and glib in itself, it's always dependent on itself. And then to compile, it only has dependencies on autoconf native, gtext, gettext, and this is all the dependencies to build glib that you have. Yeah, it's kind of a lot. zlib is required. Virtual, you gotta go and Google what all these packages are. But it's a pretty impressive tool. You can click, any one of these packages.
Do you have Fuse to try to get Windows file system support?
Sorry?
The Fuse library?
Fuse? I don't think that's, I don't know.
Also. I'm just throwing something out there.
Nope, so it's not currently listed, but I could go I could pull in a BB file that tells Yocto to go get Fuse and compile it in. Totally. Yep.
To use it with the rest of the system.
You can't?
No, I was making a pun.
Well, so if you pull in a recipe, and that recipe has a dependency on some other recipe that you don't have, that's a problem. It's not going to compile. That's why you use a dependency walker to figure out what you're missing. Okay? Pretty slick. All right, and then the final thing, this Bitbake image C populate SDK, this is an important step. This actually gives you your SDK installer. It's already 11:48, so we'll get to the end of this here. The SDK installer is what you actually extract onto your Ubuntu VM to compile software against the target. Okay? So let's look at the output of Bitbake. So Bitbake's run. Bitbake was successful. All of the code is in this folder. This temp folder has 500,000 files, maybe 1 million files if you were to check it out. And in this temp folder is what all the results of the build are. It's a ton of folders. Work is where the actual recipes are built. They're categorized. But if I go into one of these categories, here you'll see ALSA plugins, ALSA utils. In these folders is where the actual source was built. So dbus, that's an inter-process communication stack for Linux. Super common. That's how Linux and desktop environments know that when you plug in a USB device, udev monitors the USB and then publishes a dbus message and tells the rest of the desktop environment, hey, USB's plugged in. So let's go look at dbus. There's the version number that you built. And then in here is the image. This is the output of the actual root file system. So some of the files go into the etc folder, some go into user, some go into var. And it's crazy. So this image folder is what actually goes on the root file system. If you go into the deploy RPMs, here's an RPM set of dbus. And so you can use this to install it manually if you wanted to. And then if I go into temp, this is the actual log output of every single build step. Go ahead.
Right, did I see that right? It makes RPM files too, so you can load it onto a system you already have somewhere
Yep.
by taking those files to it.
Yes, sir. Yeah. So if you're looking at this folder here, we have the build folder, which is where the actual .o files and things live. We have the dbus 182. This is going to be the actual Git repository. In fact, if I sort this and then turn on hidden folders, we're going to see the actual Git repository, show hidden files. See this .pc? Dang.
It looks like Digi is really trying to play well with all of the distributions.
Digi?
Yeah, they're trying to play well with everyone, RPMs, dev files, anyone.
Yeah. In fact, as a feature of Bitbake, you can just specify, I want to support RPMs, but not IPK or OPK. Okay, so you can just specify. Bitbake supports all of them, all the major ones. So it's not necessarily Digi that did that. It's the Yocto Workflow that has made that decision. Okay. In general, everybody builds all the package types. Here's the split file. If you know about how ELF files are constructed, you split them. Anyway, in here somewhere, if I look harder, is going to be the actual source code. I think it's here, dbus. But there should be a .git file. Or if it wasn't pulled from Git, it's not going to have a .git file. But if you had it pulled from Git, you'd see a .git repo file. And you could actually check the build history of this particular package, compile or the commit history. So if we go back up to work, Again, this is a categorized list of the packages that were built. Not all these packages actually make it into the root file system. There's special rules in those .local.conf files for specifying which packages you want and which ones you don't. You can even just be like image_append and then name a package, and then it'll put it in there. So that's more documentation you have to go look at. But the fundamental point is work has all the actual build stuff. Work shared is where the Linux kernel gets built. Just happens to be in a different folder. Log is going to be macro logs. Each package itself, if you go into there, has a folder called temp, and this is where your build log is for this particular package. Pretty robust. You can see why for each build step, for each package, you end up getting a lot of output, and that's why you end up with 100 gigs of stuff once it's done. What's interesting though is this guy, deploy. This is where your results go. Yay! Go into the results folder, and we have RPM, licenses, and images. Well, RPM is just going to be a big list of all the actual deployable RPMs. Pretty crazy. You can just go right through. Qt-based fonts is in here, deja vu. And I wonder if I got, Qt fonts Vera. Oh, yes, I did. It's right there. So you can kind of walk through this set of folders, and you can know about which ones are built and which ones aren't.
Did I speak too soon? Does it only output the RPMs now?
No, wait, we'll get there.
Okay.
So we're in the deploy folder. We're in the, I just showing you the RPMs. We go to images, and then go to the name of the machine. This is a UBIFS root file system that's 84 megs that you could extract directly to an SD card and plug into that ConnectCore and power it up. So that is the set of components baked into a single bootable image. And a lot of times, if you're using VeriSite, like this one up here is a VeriSite, it has, they give you a .sd card. Makes it a little bit easier. But the instructions on the Digi website tell you how to go into the content of this folder and put it onto an SD card and boot the Digi ConnectCore. Going back into here, images, deploy. This folder is really interesting. My boss is like, Andy, man, we can't have GPL version 2 in our product. And I'm like, oh, well, that's no problem, because I can just go into this license folder, and it'll tell me all of the licenses for every single package. So if I went into BusyBox, it's going to say, boom, GPL 2. Or if I go into dbus, it's GPL 2. Go figure. It's common. What if I went to core image base? That's an MIT license. So that's very, very loose. You could, that's no problem. So it's probably, you're probably thinking, man, having them all in folders is kind of a pain. Well, there's actually a Bitbake call. I don't remember what it is, but you can be like, Bitbake, export license manifest, and it'll spit it out as like a comma-separated value file that you can just have. So that's pretty fancy. And then if we go back to the slideshow, there's a note here, Bitbake image C populate SDK. We haven't run that yet, and it would take like a half hour, so I'm not going to do it. But if I did do that, in the deploy directory, there's going to be a file called SDK. And in there, there's going to be a single .sh file, which is a script that you use to extract the SDK on your root file system of Ubuntu, so that you can then point, and that contains all of the compile tools required that Qt Creator or Eclipse would need to actually set up a build of a C++ project to run on the target. And so we don't have that folder, but if I actually ran the SDK build, we would have an SDK folder, and that's how you get your tool chain to cross-compile from Ubuntu onto your Yocto target. So that's pretty handy-dandy too. Okay, so that's enough about Bitbake for right now. Let's go through the rest of these slides and get to the end of this, because it's 11:55. So there's a bunch of useful Bitbake commands. I recommend having the mega manual. Is a really funny file that is huge. But if you went on to, they break their documentation down kind of by use case. So if you're the BSP guy, developing a BSP for your product, there's a whole guide for that. If you're a software developer, just developing code for the target, there's a whole guide for that. If you're a kernel expert, there's a guide for kernel configuration. So if you go to, if you search for Yocto, mega manual, it combines all of those. And it's super useful because oftentimes you're like, well, I don't know where this term actually is, but, and I'm not going to probably be able to pull it up. Oh, yeah, there it goes. Go T-Mobile. This is a huge document. And so if I search for like, I see in the recipe file, there's a term in there. I don't understand what it is. Image _ install. Oh, look, it shows up here. And if you looked, actually, it'd show up in like 100 different places. But here's a link to the actual definition. And then here is a description of exactly what that variable does for Bitbake, okay? And so the Yocto documentation is actually incredible. And Yocto itself has a quick start guide. And you can do the quick start without any hardware because they will build you a Yocto image and then they'll let you run the Yocto image in the QEMU Linux emulator. And so that's a pretty fancy way to do it. So the documentation for Yocto, you can do the whole thing and experiment without even having target hardware. You can build an image and then run it under Ubuntu, under a virtual machine, within Ubuntu. So, yeah, things get dicey quick, but let's throw a couple other related Yocto concepts around, and then I think that's all I got.
What was the first thing you installed Yocto on?
Ubuntu.
Oh, just like a desktop?
Yeah. Oh, no, actually I did a VM. I just had VirtualBox.
Okay, oh yeah.
Oracle VirtualBox, totally free. Just go download it. Download the ISO of Ubuntu 14.04. Set it up.
Chemo is like a VirtualBox.
Chemo is a virtual machine for Linux.
Okay.
Yeah. So Chemo, you pass it the image file and it would boot.
Oh.
Inside of Ubuntu, which can be running inside of a virtual machine.
Okay.
So that's what I meant. Things get dicey pretty quick. Did you have a question?
No, it's not. QEMU is that emulator.
Yeah,
You can set it up to run KVM to do virtualization at the hardware level on Linux. So
Okay.
they're related, but they're different.
Okay.
You want to run VirtualBox.
Yeah, you'd run VirtualBox to run Ubuntu, for example. Yeah. All right, so a more advanced concept, like let's say I had on my IMX6, there's 4 UART channels. But I want UART1 to be on pins like 34 and 35. Well, that's going to be a driver configuration. And so what you have to do there is you have to go into the Linux device tree. Now, by default, the Digi's already configured everything for that target hardware based on the documentation for that target hardware. So it's going to tell you where the LVDS header is for graphics. It's going to tell you where the Wi-Fi lives and all that stuff. And so they've configured that. But if you needed to change it yourself, there's these files called device tree sources. And you could go find them. I'm not going to take the time to dive into that detail, but they kind of look like this. And man, they are complicated. This is about as complicated as things get in Linux because it's basically a structured file of data defining device drivers. And you guys will notice right away that I'm not an expert on this part of it. But the interesting thing is that each node kind of represents a driver. And there's sets of nodes, and there can be nested nodes, and they reference addresses. There's all these magic things. 4 cells, 32-bit values, 1, 2, 3, 4. A cell property. Who knows what that is? Nobody, because nobody knows what that is. But the important thing is, here's how you figure it out. What on earth is allowed in 1, 2, 3, 4? I have no idea. Maybe another number is allowed. Maybe it has to be 1, 2, 3, 4. I'm not sure. So what you have to do is you have to understand which driver they're talking about. In this case, the master node, and this isn't even a real example. So there'd be a keyword in there somewhere that says something like, VPU. And that would be the floating point unit you could configure, for example. Or maybe it's some GPU term, or I2C is in the term. What you find then is that it's an I2C, let's say. So then you need to go understand which driver that's actually talking about. And once you know which driver it's talking about, oftentimes I'll just go into the driver folder and I'll just grep. And if you do a grep for a cell property, you're going to find where it's actually used in the driver by name. And so then you can go look at that driver code and say, oh, I see where they're loading the device tree binary configuration. I see where 1, 2, 3, 4 is actually getting used. And that's how you would go about changing this file to have different configuration for that particular driver. Okay, that's way more deep than we needed to go, but that's how you would do it. And then basically they're DTS files. That's all you got to know. They're DTS files that get compiled into a DTB file. And if you remember back to the beginning of this presentation, when U-boot launches the kernel, it points out the kernel itself, the binary for the kernel, the root file system, and a DTB compiled device tree binary, which is, this is the source code version of it, but there's a compiler that turns it into a binary that the Linux kernel then loads. Go ahead.
Those can be loaded at runtime too.
Yes, they are loaded. They are U-boot loads them dynamically at runtime. So what's interesting is like this development kit, there's like a couple flavors, and Verisite has a set of U-boot modifications to the U-boot source code, so that when U-boot fires up, it actually knows how to detect what hardware is on the board, and then based on which board it detects, loads a different device tree binary to load for that actual board. So that's why Wi-Fi just magically works with the same sum on 3 different dev boards. It's kind of crazy. All right. So licenses, we could talk about this for a long time, but this is a common topic at your day job if you end up doing embedded Linux for a product. Really where you want to be very, very clean about it, is to the right of this line. Now GPL v2 is a little more restrictive. GPL 3 you typically don't have to bother worrying about. But everything from here over is like pretty much wide open. You never have to release your source code. You can change it. Typically if you change the code, you have to provide the changed code to the internet, stuff like that. But we can talk about that for a long time. There's a lot of buyer beware mentality surrounding embedded Linux, but Yocto is helping make that less of a problem. And then another cool thing about Yocto is you can learn a lot about how it works if you just go look at the Git history of the sources and see what people are committing. And you'll notice that there's actually a huge community of people behind it. Everybody knows Git. Qt framework's really cool. So on our example, that dartboard, or sorry, that ConnectCore does support the Qt framework. And so to pull that in, let's go find that quick. ConnectCore, going back to the root, going to the conf file at the root of the build directory, the actual outputs directory, there is a local.conf, edit with gedit, go to the bottom. I've configured this, extra image features. If you go look through that ConnectCore documentation, they tell you, they hand this to you. They say, hey, you could put in things like DUI-Qt or DUI examples, and then that will cause the build system to go get the Qt framework and then configure it for this target, and then you can run the Qt framework on your target. Qt framework is basically like this giant software stack to make a lot of the common things you have to do on a desktop very easy. So file I/O, talking to a serial port, it's just abstracted into these nice classes. Q serial port, you know, Q dbus exists if you want to use dbus. There's like Q audio output. So you don't need to know anything about how the audio actually works on the system. You just call into Q audio output and you say, I want a sine wave at 350 hertz. And then Qt takes care of the rest. So Qt is an open source stack. If you change it, you probably have to get a professional license. That costs money. It's kind of a dual license type thing. But Qt is very, very popular for embedded systems. Qt primary use, you probably know about, is in the UI space. That's actually a huge UI stack. But it also gives you a lot of like actual classes that have nothing to do with UI development that help you in embedded Linux. So the Qt has this new framework called QML. It's also really cool. We're doing a lot of that at Minitronics these days because it's just the fastest way to get an embedded system UI going. And so it's pretty powerful. And it's like OpenGL accelerated automatically out of the box and stuff like that. So it's very performant. Going back to the slideshow, I think I'm at the end of this. Hey, cool. Any questions? On the internet. Sure. If you search for a Linux cartoon, you'll end up with a lot of funny stuff. Thanks, guys. That's the end of my talk. That's about the end of it. Is there any questions or anything that anybody wants to? I suppose I'll leave that around. Yeah, go ahead.
That Digi web page you had up with the cool graphics that was showing the
Encryption, the encrypted file system, and yeah.
What is that?
It's the trust. If you just Google the ConnectCore 6UL is the target product, and then in that product's official documentation is that website that we looked at, and in there it's called the Trust Fence section. They have really, really cool graphics showing you how encrypted boot works, stuff like that.
Something about the hardware that allows that.
Yes. In fact, it's really clever. Let me tell you, a hell of a lot of thought has been put into it. It basically surrounds, there's an encrypted key there's a key that is burnt into every IMX6 out of the box, and you can't change that. And then basically there's a workflow for using that key plus a certificate that your company owns to produce binaries that are encrypted that only that IMX6 knows how to decrypt and run. Yeah. So you cannot boot the kernel without that key sign, and without the certificate and the private key, you can't even create binaries that will run. And so the workflow is very, very secure, and you can promise to people that there's no way a virus takes over the system and puts binaries that are not allowed onto your boot image. And so that, like, if the file system's locked down, there's just no way for a virus to get in there and start running stuff that's no good. It's pretty sweet. And so you can make your file system read-only and make that even better. So yeah, there's a lot of security technology, the PhD level stuff that went into this IMX6 to make that work right.
How do you incorporate your own executables?
I'm sorry?
How do you incorporate your own code?
So what you have to do is there's a build step, and they actually help you with that in the documentation that takes the certificate for your company, and it uses the public key information out of that to produce the encrypted binary. And then the private key signatures are put onto the target in an encrypted way. And then that's how the target knows how to decrypt the stuff. But at no point in time do you actually release your company's private key. That's very slick. And the graphics that I showed you walk you through that whole thing. It's actually like remarkable.
But Andy, what about, somebody that's just doing a home product versus
Yeah.
a company? You can go get your own certificate.
Heck yeah. If you want to just go make an account, you can go to a certificate authority and issue yourself a certificate. And then I don't even think you need a certificate authority technically. I think you can just make it go on your own. But the professional way is to use a certificate authority so that you can authenticate that the public key is valid before you boot the system.